All right, so what about class 1 carbonyls, carboxylic acid derivatives? Can they react with organometallics, Grignards, and organolithiums? Absolutely. So here's our first one, an acid chloride reacting with a Grignard. Let's draw this mechanism together. Acid chloride reacting with a Grignard. First thing to do, attack the carbonyl carbon, like so. Grignard had 3 carbons. Make sure 3 carbons get connected. Grignards are famous for students gaining and losing carbons. Don't be one of those. What's so different about the carboxylic acid derivatives and things like aldehydes and ketones? They have leaving groups. This thing is a good leaving group. Aldehydes and ketones do not have good leaving groups. So when you get here, fold down and kick out your good leaving group. And you make this thing. This thing is a ketone. Do Grignards react with ketones? Absolutely. We just finished studying that. Grignards do react with ketones. This is the reaction so nice, it happens twice. Attack the carbonyl carbon. Like this. And you get here. This thing. Then and only then do you do your acid workup to protonate your O-. You get an alcohol in the end. Is this a good way to make a ketone? No. Is this a good way to make an alcohol? Yep. So acid chlorides and esters and even amides, although we won't see many examples of that, amides that do not have acidic hydrogens, note, amides that do not have acidic hydrogens, these things can react with Grignards not once, but twice to give you an alcohol. You cannot stop at the ketone. It's not good to make a ketone. It needs to react twice. Note that in the alcohol in the end, you have 2 identical legs on your alcohol. Where did those 2 legs come from? They were part of your Grignard. They were your Grignard in the beginning. There's our acid chloride and Grignard, made a ketone, but that was, a ketone was just in the process. It was one of the intermediates on the way to make an alcohol. This is the reaction so nice it happens twice. You should expect the same thing with an ester. The reaction so nice it happens twice. Can Grignards react with carboxylic acids? Well, not exactly. Grignards are strong bases, and they react with carboxylic acids to deprotonate them. First, make an O-, a carboxylate. As it turns out, once you make that carboxylate, carboxylates are unreactive toward Grignards. This carbon of your carbonyl is too stable, it's not partially positive enough for a second equivalent of Grignard to react. So even if you add lots of Grignard molecule, you're not going to get any reaction beyond this. However, are there any organometallics that are more reactive than Grignards? Organolithiums are more reactive than Grignards, so organolithiums can react further. As it turns out, they make that product. Is that exactly what you would have predicted? I bet not. Let's draw a mechanism to see how that one happens. Organolithiums reacting with a carboxylic acid. Organolithiums are strong bases, just like Grignards. They're even stronger bases than Grignards. Attack the hydrogen of your carboxylic acid to make this carboxylate. When a Grignard did that, we said a Grignard is not strong enough to react with a carboxylate. The partial positive here is not enough of a partial positive for a Grignard to react. Oh, not so true when you have an organolithium. Organolithiums are crazy reactive species. So that organolithium can and will attack the carbonyl carbon of your carboxylate. And you make this wacky compound, this crazy double negative. Double negatives ain't no good, but organolithiums are fierce enough to make them happen anyway. You make this double negative. This thing is not going to undergo any further reaction until you do your acid workup step. Because this thing cannot fall down and kick out a leaving group. You would kick out a C minus, an O2 minus. I think not. You can't do anything further. The lithium cannot displace anything else off of this. So you protonate both of those O minuses. I'm going to draw it like it happens in one step, but you know that's not true. Protonates both O minuses to become this thing. This thing is known as a hydrate. Hydrates are things that exist commonly, but they're always in equilibrium with the ketone version. I said that in a weird way, I know. The hydrate is always in equilibrium with the carbonyl version of the same molecule. Equilibrium generally favors formation of the ketone. So you're going to protonate to make this hydrate, and then that hydrate will do an equilibrium thing to yield this ketone. The exact mechanism of how that happens, we will learn, and we will learn very soon, but we're not going to go over it right this minute. You lose water in the process. I'll talk you through the mechanism. I don't know why I'm deciding to do this, but one of these O's gets protonated to make a water, fold down and kick out that water. Then you've got a C double O with an OH, and then deprotonate that, and you've got a ketone. Hydrates and ketones are always in equilibrium, but in general, the ketone is favored at equilibrium. We will talk more specifics about hydrates in our next chapter. So rather than making an alcohol over here, as you may have predicted, because Grignards with all the other carbonyls have made alcohols so far, rather than making an alcohol, when you react an organolithium with a carboxylic acid, you make a ketone, because that acidic hydrogen screws up the whole deal. What if I tried to react a Grignard with a nitrile? Can Grignards react with nitriles? Let's draw it. A Grignard with a nitrile. No acidic hydrogen, therefore attack the carbonyl carbon. Yes, I know it's not really a carbonyl. That's okay. It behaves the same way. Grignard had 3 carbons, 1, 2, 3 carbons get attached to the carbon that was the nitrile carbon. You make an N minus. As we just saw in the last example, a Grignard is not strong enough to attack something that's already negative to make a double negative. Grignard ain't no good at that. So instead, you're ready for the acid workup step. The first thing that happens in acid workup, protonate that nitrogen. I got a little misguided. It's going to the H. Protonate that nitrogen to make this. This is a brand spanking new functional group. Who would have thought that we're still learning new functional groups at this point in the game? This is an imine, an imine. We're going to talk quite a bit about imines when we talk about the reactions of aldehydes and ketones beyond organometallics. But imines can be hydrolyzed to form carbonyl compounds. This imine is going to be hydrolyzed to form a ketone. This NH4 is produced as a byproduct. This reaction of an imine being hydrolyzed to a ketone is equilibrium. It's reversible. It depends on whether you add more ammonia. I know that's ammonium. It depends on whether you add more ammonia, whether you're going to favor the imine formation, or you add more water to favor ketone formation. We're going to control this equilibrium process with Le Chatelier's principle. We will talk more details about this imine hydrolysis, the forward and reverse reaction there, but not until we finish organometallics. After the Grignard attacks, we get an N-. After the workup, we get an imine, and that imine may hydrolyze to a ketone. For now, we're going to say it always does, but there is a way you can potentially stop it at the imine. All right, here's a giant roadmap of lots of reactions of Grignards. Let's work on it together. So I cheated this time and drew it all out before we got together. I encourage you to please pause the video here and try these on your own. If we were in class together, I would force you to draw these while I come around and check. But alas, here we are. We'll do them together. We'll start over here to the right with this Grignard attacking my ketone. Grignards are famous for, Grignards are famous for students gaining and losing carbons. My ketone had 3 carbons with the oxygen in the middle. 3 carbons got added, the oxygen on the middle carbon. Then I protonate my O-, and it's done. I made an alcohol. Grignard attacked my ketone. I made an alcohol. Up next, Grignards can attack epoxides as well. And because they're strong bases, when they attack epoxides, they attack the least substituted side. So my Grignard gets attached on the least substituted side, and my oxygen goes next door on the neighboring carbon. I put in a wedged carbon here just for fun. This carbon was not involved. This stereochemistry better stay the same. Protonate the oxygen that you made, the O- that you made. There's my alcohol from a Grignard busting open an epoxide. Students typically think this example is toughest and most tricky, so we're going to skip it for now and hop right over to the next one. If we had gotten to do the Grignard lab, we would have done this exact experiment where our Grignard attacks the carbonyl carbon of CO2, dry ice, solid CO2. You get an O- out of it, and then you do some acid workup to protonate that O- to make benzoic acid. We would have done that exact reaction to make benzoic acid. I think I want you to find an internet video that does it and show me. Moving on around, up here to the ester. Grignards can attack the carbonyl carbons of esters. To give you this intermediate. What's so different about this intermediate versus this one or this one or this one? Esters and other acid derivatives have leaving groups. So I fall down and kick out my leaving group, my weakest base, my best leaving group, and I get a ketone. Ketones can also react with Grignards. So you're going to attack again. If a ketone can react with an ester, you bet it can react with a ketone because a ketone is even more reactive than an ester. So you cannot predict this ketone as the final product up there. It has to react twice. There's no option. Then you protonate the O- that you made, and ta-da, you get an alcohol. There it is. As I said just a minute ago, students find this example most confusing, most tricky. It is not difficult at all. It's very straightforward once you get one little thing. Acids and bases will kick your butt if you'll let them. Grignards do not generally attack and become attached to alkynes. But if it's a terminal alkyne, like this one is, a Grignard is a strong base, and it can deprotonate a terminal alkyne like that. My Grignard from the beginning becomes benzene, plain, boring benzene. But my terminal alkyne is now negatively charged. You will sometimes see it drawn that way. You will also frequently see it drawn this way, as if we made a brand spanking new Grignard reagent. This benzene is no longer useful whatsoever. It will not show up in my product at all. But this Grignard is useful. It attacks the carbonyl carbon of that ketone that I added. Like that. And then I protonate my O- to get my final alcohol. Whew. It's not tough, but that first step is tricky. Acid base happens first, it happens fast. That's the only option when you put that Grignard and terminal alkyne together. Got it? Good. Starting with that first example. First, you recognize it's an alcohol. We've gone over multiple ways to make alcohols using Grignard reagents, so now we shall put some to use in a synthesis. One way is a Grignard can attack a carbonyl compound. So I could imagine making this bond through a Grignard attacking a carbonyl compound. This carbonyl being attacked by this Grignard reagent. I probably won't write this on every example we're about to go through because it's all the same. But remember, you will have to add the Grignard and carbonyl together and then always do an acid workup next so that you get a neutral alcohol in the end. Is that the only carbonyl option for this one? Yes. The other option that students may think is valid is having a Grignard and carbonyl within the same molecule and trying to do an intramolecular reaction, but that's not a valid option to have a carbonyl and Grignard within the same molecule. That's a no-go. Grignards react with carbonyls, but they also react with epoxides. Could we make this molecule from an epoxide? Imagine that bond used to be my epoxide bond. This is the bond that the Grignard would make from busting open the epoxide. What epoxide? Well, that epoxide. This epoxide reacting with this 2-carbon Grignard would absolutely add together to give you this after you did some acid workup. Yeah? Moving right along to our next example. This is an alcohol. It's a tertiary alcohol. There are multiple ways to make this alcohol from a Grignard reacting with something. One way is a carbonyl compound reacting with a Grignard. Here's one option. I think I made too many carbons. Let me count. 1, 2, 3, 4. 1, 2, 3, 4. Yep, I did. That one doesn't count. Whoopsies. I make mistakes too. That's going to react with a 4-carbon Grignard. This 4-carbon Grignard attacking that carbonyl. This 4-carbon Grignard attacking that carbonyl gives me that alcohol after acid workup. As it turns out, If I tried to break and make that bond, it's the exact same reagents to make or break that bond. Is there another carbonyl compound that I could add to a Grignard to make this? Uh-huh. I could imagine this guy being my Grignard, reacting with this ketone. Why did I draw this in such a funky orientation? It's just a 9-carbon ketone. Well, it's just easier to make sure it stays in the same orientation because then I don't have to count quite so many times, because Grignards are famous for causing students to add and subtract carbons. Be wary. Don't do that. Can I use another carbonyl compound to make this Grignard? Ugh, yeah, I can. When I notice that this leg and this leg are identical, both of those are 4-carbon pieces. There are 2 identical legs there. That tells me a 4-carbon Grignard could have attacked a carbonyl that had a leaving group. The leaving group could be an acid chloride, it could be an ester, or it could be an amide, as long as the amide does not have an acidic hydrogen. But an acid chloride and ester are the 2 most common ways, the most common derivatives, acid derivatives, to make alcohols from. So noticing that there are 2 identical legs, it could be an acid derivative that has a leaving group. I think that's all of my carbonyl options. Could I make this thing from an epoxide and a Grignard? I'm going to draw my original molecule again because it got a little crowded up there, a little messy. So there's my original molecule, and this time I'm going to try to make it out of an epoxide. Remember, epoxides, the oxygen has to have been connected to the next door carbon. And the bond next door to that is the one that has to have been made between the Grignard and the epoxide. So there is my Grignard and epoxide that would react together to make this alcohol. As it turns out, that's the only option, because if I had tried to connect over here to that carbon, it's the exact same 2 reagents. And if I tried to connect down here, that's a benzene. This cannot accept another bond. So this is my only epoxide option. I think students generally think epoxides are the toughest, the most tricky. My best piece of advice is try to get in the habit of imagining that oxygen is ... bonded to the neighboring carbon in what used to be an epoxide, and then squiggle the bond next door to that, because that's the bond that the Grignard had to have made. That way, you know that when you have the Grignard and epoxide drawn, it will force the Grignard to attack the least substituted side, which is a mandatory thing when Grignards and epoxide react together. Did I mess with any of this down here? No, that was bonded to my carbon that was never even involved in my reaction whatsoever. That's my best advice for epoxides, but sometimes they are tough to see. I get it. Let's do another alcohol synthesis. Imagine this alcohol used to be a carbonyl. I could imagine making that carbon-carbon bond using a Grignard, a 3-carbon Grignard attacking a 5-carbon aldehyde. I should have said this already, but I encourage you to pause the video and attempt to draw all of the possible options for these before we do them together. Nevertheless, we're going to do it together. I'm going to note that this is the red synthesis because that's going to apply to a question I will ask. Another carbonyl option. Carbonyl here, imagine breaking and making that bond. This is my carbonyl reacting with this Grignard. This is blue, if you can't tell. That's all of my carbonyl options for this one. But I do have epoxide options, like this one. That's green. I could also imagine an epoxide on the other side of the molecule. So I could use this epoxide and that Grignard that's purple, if you can't tell. The colors are relevant for me to say, design a synthesis of this alcohol beginning with ethyl bromide as your only source of carbon. Design a synthesis for this alcohol beginning with ethyl bromide as your only source of carbon. In my opinion, the best approach is to first decide which two big pieces you're going to need to react together, meaning color-wise, and then break it down by synthesizing those pieces from ethyl bromide. We will go over this together, but not in this video. We're moving on to our last example for this one. We want to synthesize 3,6-dimethyl-3-octanol. 3,6-dimethyl-3-octanol. We are forced to synthesize this thing from 2-methyl-1-butene. So the first thing I pay attention to is this thing has 5 carbons and this thing has 10. And I'm wanting to make 2 of these combined together to make that. I need to make a carbon-carbon bond, and I hope the first thing you reach for is a Grignard something to make this carbon-carbon bond. Like all the others in this video, I encourage you to pause the video and attempt this on your own, but I have to keep moving. I'm going to try to figure out which bond I need to make. I see carbon 5 stuck out here like a little flag. This looks like a little carbon 5 flag to me. So if I count the remaining numbers, that looks reasonable. This looks like another carbon 5 flag waving. So that seems reasonable. So that tells me this is the bond that brought those 2 pieces together. Is there an oxygen on the carbon connected here? No. If there was an oxygen directly connected to either of these carbons, that tells me it came from a carbonyl. Since there's not an oxygen directly bonded to either of these carbons, and the oxygen is next door, that tells me it came from an epoxide being busted open by a Grignard. In fact, it's this epoxide that got busted open by this Grignard. So now that I've done the hard part and broken it down into the 2 big pieces, I need to show how this piece could have come from this alkene. Hopefully you remember how to make an epoxide. MCPBA. Added to an alkene. Hopefully you remember how to make a Grignard. All Grignards come from alkyl halides. Add some solid magnesium to your alkyl halide and you get a Grignard. How do I make that alkyl halide from this alkene? Well, I'm wanting it to be anti-Markovnikov, and anti-Markovnikov can be accomplished with HBr and peroxides. Is that the only way to make this alkyl halide from that alkene? No. You could do anti-Markovnikov alcohol and then maybe substitution with PBr. Maybe you remember that better. Maybe you don't remember that as easily. It's up to you. You just got to get her done. That's all for now. Peace out, yo.